Please welcome Amir.
Yeah. Thank you, Rich. So today I'm going to talk about temporal difference networks. And this is going to be the outline of my talk. I'm going to talk about the motivations behind it and how to ground knowledge in experience, temporal difference networks, and then an example, which is the bit-to-bit grid board. So talking about the motivation. So the thing is, despite many years of research on representation, there are no types of representation that can be comparable to a richness of a child's understanding. And this is something that we would like to have. So let me give you an example. So think about a balloon or a drinking glass. And we know so much about them. We know about their size and shapes and their textures. And we know what would happen if like the wind blows, what would happen to the balloon or a drinking glass. This is something so intuitive to us. And this is not something that we explicitly been told, but we learn it from our everyday experiences. Though it is only learned from our experiences, that knowledge is represented to us in an accessible way that we can quickly check its validity or use it for deeper reasoning. So the idea is we want to use predictions as knowledge. And there is this predictive representation hypothesis that's saying representations of a state of world that are in terms of predictions of upcoming experience will generalize particularly well. And I'm going to talk about the word experience in the next slide, but let me give you some intuitions about what it means. So think about the example of my keys are in my pocket. This is one statement about the world. We can rephrase this statement into a prediction by saying, if I put my hand in my pocket, I will detect my keys. And this is actually the same statement and has the same meaning somehow, but we used prediction instead of just simple statement. So what we can say is, in other words, we can say knowledge is prediction of experience. And we are talking about the experience as well. So by having knowledge, by setting knowledge as a prediction of experience, we can enable the agent to do verification and self-maintenance. So maybe I should put this before, but so the setup is something like this. We have an agent, and we have an environment, and the agent can affect the world by doing an action, like moving an arm, by looking or moving the eyeball, whatever action you can think of. And after doing an action, the environment will give us an observation, a new observation that we can see and use for further purposes. So the agent performs an action A, receives an observation O. So earlier we talked about experience, and we can call experience a sequence of actions and observations, like O1, and then we do action 1, then O2, action 2, and then there is this notion of time. For instance, we are in time step 2, and from time step 2 is in the future. OK. So what we are trying to do is ground knowledge in experience. And what does it mean is to represent the agent knowledge of the world in terms of agent's experience. So what was the experience? It was the sequence of actions and observations. So what we need to do is to represent the knowledge in terms of observation, actions, and time. And by doing this, putting the board knowledge in terms of observation, actions, and time, we can have a representation that constructed through interaction with the world, because interaction means doing actions and getting observations. And it's modifiable and extensible with new experiences So if we get new experiences, we can refine our knowledge and what we know about the world, or something is no longer true, we can discard it. And it's also, most importantly, it's verifiable through interaction with the world. So the agent can verify its own knowledge because it's in terms of its own action and observations, it can do them and simply see whether those predictions are true or not. Those observations going to happen or not. Okay. So the next step, we are assuming the predictions are questions and answers. So let's get back to the example that we had. We had the statement of my keys are in my pocket. And we changed it to and we rephrased this statement to a prediction of if I put my hand in my pocket, I will detect my keys. So what we like to do again is to rephrase it again. And instead of having the prediction this time, we want to rephrase it to question and answer. So we can say, if I put my hand in my pocket, will I sense my keys? So this is the question. And the answer to this question is going to be the answer part, whether it is there or not. And let's think the key is in my pocket and I can sense it. So the prediction of if I put my hand in my pocket, I will detect my keys is a true statement, true prediction. Okay. And so let's get to the temporal difference networks. So in temporal difference networks, we are trying to rephrase the problem of prediction to questions and answers. And we can see, you can say question represents the meaning of the prediction, while the answer computes the estimate value of the prediction. And we are using TD learning. And as you may already know, TD learning is about learning a guess from a guess. And before TD networks, these two guesses were the same quantity. And with TD networks, what we are trying to do is we can guess, still do this guess, learning a guess from a guess, but these two quantities can be different. And that's the whole idea behind temporal difference networks. So let me give you some examples about question network. So let's say we have an observation, and we have two predictive nodes, and predictive node 1 is connected directly to the observation, and predictive node 2 is connected to predictive node 1. So what is the meaning of this predictive node 1? It's directly connected to observation. We are at time t. So what it's trying to predict is what will be the value, what will be the observation at time step t plus 1. And for predictive node 2, we have this what will be the value of predictive node 1 at time t plus 1. So these are unconditioned. In the next example, we have conditioned question networks. So we have predictive node 1 here connected to observation again, but with condition of action A2. And we have predictive node 2 connected to observation with condition on action A1. So for instance, predictive node 2 wants to say what will be the observation at time t plus 1 if I choose the action A1 at time t. And this is the same thing for predictive node 1, which is trying to say what will be the observation of at time step t plus 1 if I choose action A2 at time t. Yep.
Was the previous example marginalized over the policy or the action?
So it's not about policy or actions. It's just about time here. There are no actions involved. So we have observations, actions, and time. So in this example, we are only dealing with time and observation. Yeah.
What do the arrows mean?
It means that it's trying to predict the value of where the arrows is heading to.
Here the arrows, in the next slide, the arrows had an annotation like A1, A2.
Yep.
Is that the same type of arrow?
Exactly, but these are unconditioned. They are not conditioned based on any actions. So the thing is, So if we are doing it in like a real scenario, at time t, we are either going to choose action A2 or A1. Just one of them, right? And the target for that action will be chosen because that action is chosen on that time step. It will get clear when I get to the example. And OK, so the last example is this network. So we have the same scenario, but now we have another predictive node which is connected to predictive node 2 and has the condition of A3. What it's trying to represent is what will be the value of predictive node 2 at time t plus 1 if I choose action A.
Should be A3.
A3 at time t. Yep. OK. So it's all clear? Yeah, OK. So before going to the example, let me talk about a little bit about the TD semantics and extensive semantics of these nodes. As you recall from the last slide, we had this predictive node of 3 that is asking the question of what will be the value of predictive node 2 at time t plus 1 if I choose the action A3 at time t. That one is A3. But the extensive semantics can be what will be the observation at time t plus 2. We no longer have t plus 1. We go one step further. If I choose action A3 at time t and action A2 at time t plus 1. So what we are actually doing is in TD semantics, we have this interpredictive relationships in question network. But with extensive semantics, we are unrolling this to get to the observations and actions until we get to the observation. We are unrolling this interpredictive semantics. OK. So we need to talk about the answer network as well. This is the answer network computes the estimate value of the prediction based on the targets specified by the question network. So if you remember that example that the arrows were pointing at observation from predictive node 1 and 2, and from predictive node 3 it was pointing at observation at predictive node 2, now they are reversed. So it means that the target for predictive node 1 would be observation if we do action A2 at time t. And this is the same thing for predictive node 2 and 3 based on their semantics in the question network. And I'm going to talk about the TD network algorithm. So the thing is, the notations may be a little bit different from what you have seen before. I use the notations in Temporal-Difference Network Thesis by Brian Tanner. And these are 5 important steps that we are doing. So imagine we have n number of predictive nodes, and they are numbered from y0 to yn minus 1. And we have m as the number of features. I'm going to talk about how we can select the features but in the example, but just keep that in mind, the number of the feature is going to be m. So if we choose action AT minus 1 if we choose action AT and observe OT, this is the first step that we are doing. We choose the action, we get the observation from the environment. And then we create the feature vector. The feature vector created based on the most recent action that we did, the observation, and the previous predictions that we had, Y's. And we calculate the new predictions by using the weights and the feature vector. We multiply them. And we use this sigma function to transfer them into the predictions. So this sigma function can be identity. So it's just the identity. Or it can be like sigmoid if you want to have the values between 0 and 1. And then we calculate the targets based on the question, based on the answer, based on the semantics in the question network. And we also calculate the conditions. And this condition is going to be either 0 or 1 based on whether do the action conditioned on those connections between predictive nodes or predictive nodes and observation. Yep.
5 minutes.
OK. And then we are going to update them based on, we are going to update the weights based on the step size, the TD error, which is the predictions, which is the target minus the predictions, conditions, and then multiply it by this partial of y to the partial of wt, which is depends on what you would choose as the sigma. So let's get to the example. So we have this very simple bit-to-bit grid board, and this is only about in this world we only have 2 possible actions. We either go forward or right, and there are only 2 possible observations, either 0, which is clear, or blocked, 1. And as you can see, the agent at the very beginning,
Clear and block.
clear and block, it means that if it's clear, then you can go there. If it's blocked, it's black on there, and you cannot move to that point.
The cell in front of you.
Exactly. So the agent only sees in front of it. So in the first picture, as you can see, the agent is pointing at bottom. So it sees a white cell, and the observation is clear, and the agent and the action that we are choosing is right, for instance. And as you can see, the agent now facing to west, and again the observation is clear. And if we move forward, it's possible for us to move forward. And yes, okay. So this is a very small experiment. By no means it's not limited, because we can have infinitely very big scenarios. And the good thing about it is only 2 bits of sensation, 1 bit of sensation, 1 bit of action, and that's the simplest possible thing that we can have. So what we designed as a TD network for this is whether the observation is going to be blocked as the yep.
What is sensation and what is observation?
They are actually the same thing. We sensing, yeah, I shouldn't use the sensation. That's the observation. So the observation is going to be whether it's blocked or not. And we have these predictive nodes of y0 to y6 here. For instance, y0 is conditioned on going forward and predicting the observation. y3, for instance, is moving forward to predict the value of y0 as the TD semantic. And as the extensive semantic, we can say y3 is predicting the value of observation at time step t plus 2, because we are 2 times far from the observation. The depth of this node is 2. OK. The only different thing here in this experiment is we are not only using the most recent observation and action. We are using a history of it. It's like, for instance, we have 5 of them or 6 of them as the length of the history. And I'm going to show you a little bit about this. Where is my mouse? So it is still work in progress, and I didn't know what are the exact values for the experiment in the paper was. So I'm replicating a work here, and this is the work in progress. So we have the world there. We have 2 possible actions, and these are the actions and observation history that we have. They are indicated over there. So let's move around a little, and I'm going to talk about this part. So if we turn clockwise, now the agent is moving, looking at the west side. But the only thing agent knows is these 2 histories and its own prediction. So it's not like that we are looking directly at this great world. The agent only knows its history
So
And
History AT1, AT2, what's the history?
no, that's AT minus 1, AT minus 2, AT minus 3.
Oh, A. So what is it known?
And the observations of observation T minus 1, observation T minus, at time step T minus 1. So this work has been learned for many time steps, and it's like after 20 million time steps that we are here. And we only captures the last, we only keep the last 6 observation and actions. So I need to do it a little bit quicker. Yeah, okay. So as you can see, these white and black semantics, black bars, they have the meaning of whether it's going to be blocked or not. So this one, for instance, is predicting if we move 1 step forward. This one is predicting if we move 2 steps forward, what we are going to see. As you can see, some of them are not white or black, they are gray, because they are the probabilities of seeing black, seeing blocked, for instance. And what we can see here is the agent can understand if you move forward, it knows that the probability of seeing a wall getting higher and higher. When we are here, the agent is somehow sure that in the next time step we are going to see the wall. But the agent actually doesn't see this. It's in terms of its own prediction. The only thing agent knows are those histories and the predictions being calculated over time. So if we go here, step forward, and we turn, it knows that, so if it's blocked, it's going to be blocked forever. It's not going to be any better if you move forward. And it remembers, like, so I turn from here, so it's black or very gray, and these are white spaces. So I can move there and go. So no. So again, so these are not being learned very good. I need to tune my parameters. But as you can see, again, the head is clear, and it knows it's going to get to the wall somehow, but it's going to be clear for some time. OK. So very quickly, I need to recap this. So the conclusions are, by grounding knowledge in prediction, we make the knowledge meaningful to the agent. And the agent can learn and verify this knowledge. However, it's harder for us to interpret and explain this. We need to see the world through the agent's eye. And this idea is somehow similar to the idea of learning the model of the world's dynamics. And the next step is going to be using temporal abstraction, which is already done by temporal abstraction in Temporal-Difference Networks thesis, and having some stochastic sensations, and maybe discovery, which the thing is, what we did was actually designing the TD network. And that part was hard-coded in the system. So the discovery would be finding interesting TD networks for the task that we are doing. And that's it.
So we have 6 minutes and 30 seconds for questions, and then people should not feel obligated to stay after that. If you want to talk longer than that, you can hang around.
Yep.
Okay. In the diagram you showed, it shows this nice GUI, and the agent is making predictions about the future. What actions were they about?
Let me bring that one. You mean?
Like, how did you generate this? You know, the agents now, I can imagine you could ask, what would happen if I went forward, to the right, or to the left? But then, what's the next prediction about? Is it about going forward and then forward again, or is it
So it depends. Like, so for instance, this one.
Okay. Yeah.
So we step 1 step forward,
Yeah.
and then we turn right.
Okay, it's about all the actions. Got it.
So it's 2 step forward and turn right. Or, for instance, this one. It's either going to be the observation, or we do 4 steps of turning. So we 1 turn, we are looking here, one turn, and then again here. Yep.
This is after a few thousand iterations.
Many more.
Were you driving? Or who's driving? Were you trying every action?
Yeah, it's randomly selected. Only 2 actions with 50%. We are going to do the right action. With 50%, we are moving forward, and we are learning about them.
No direction, it's just random.
Exactly. So
Exploration.
the whole point is the only thing that agent sees is its own observation. It has no idea of what we have, like west and north, or like the position in the grid world. In that point in time, the agent sees it's clear, I can go. That's the only thing agent knows. Yep.
Two questions. So are these predictions tied to a policy or they're not tied to a policy?
It's a random policy that's generating them, but we are not doing any kind of control here.
So it's
But
like
are the
complete-
predictions tied to particular actions?
Yep. So as I said before, for instance, this prediction is only about if I move one step forward. Actually, there are various predictions for this line that can be. We can, for instance, go here and then do 2 turns and looking at this. But these predictions are based on those actions. That's what the meaning of those conditions are. Yep.
So it's a complete model of the world, and it's not just one step. So if you take 2 steps, you will see something like that. So it's more
Yep.
than one step.
Exactly.
The
That's
paper is from 2006.
5. Yeah.
5. So 13 years have elapsed, and it seems pretty good. What has happened?
I have no idea, but it seems like a very interesting subject to me. And we also have GVFs in between, and we have many off-policy algorithms that can help us like learn many of these. Yeah, Martha.
I'll just answer Mohamed's question a little bit. We're working a bit on extensions of TV networks, so you should talk to Matthew Schlegel.
Yeah, the GVF networks and
Yeah.
yeah. I completely forgot about
The
the
names
GVF.
have changed in 30 years.
Somehow. Yep.
It took us so long to come up with that name.
I have 2 questions. and
Sure.
Probably naive. Can you go back to the TVNet algorithm?
Yes.
What are these conditions? See, maybe you said them and my ears just didn't hear it.
I didn't
What is-
explicitly like talked about them. I only referred them to like these things. So for instance, when you want to learn about predictive node 3 at time step t, you need to have this action A3 happened to use the value of predictive node 2 as the target. So if
So C would be 1 if you take action.
action 3 and C would be 0 if we take any other actions.
Okay, second question though.
Yep.
You went, again, I walked in, I think, on the second slide, it's probably me, but go back to this place, you're talking about verifiable all the time, and I'm having a little bit of trouble with that. Because unless your environment is, is stationary in time, you can go back and do the same thing, and not the same thing may happen, right? So either it's time varying or maybe be a stochastic environment, so I'm not on this picture, but you're always talking,
Yes.
several times you mentioned that that's a great thing about this, but that's only under certain conditions, I would think, or I don't understand how you're
So,
trying to verify it.
so the thing is, this environment is completely deterministic. But even if it was stochastic, so the expectation were true, right? So the thing about verification is, I'm predicting this is, for instance, black, this one. I go forward like 5 time steps and see what the value of that observation is going to be. So because it's in terms of its this agent's observation and actions, the agent can go and verify it. But if we like engineer something into the system, then we would lose this verifiability because the agent might not know exactly what you were trying to do, trying to design on the system. It may be like a higher intuition of yourself as the designer. But if we are doing it in terms of the agent observation and actions, then we can go and verify it.
Provided the environment hasn't changed. You can go again and it may not be the same thing, and so you're not going to be able to verify, right?
Yes.
I mean, you go, you see something else, but that may be more of the rule than the exception. I mean, maybe you can verify it see this thing with a particular probability distribution of something like that, a stochastic environment. But maybe not, so I'm just, that was, sorry.
So that's true. Let's say we remove that object in the middle. And the agent, we learn this object is in the middle, and we just suddenly remove it. That's something stochastic, right? So after a while, the agent what can agent do is to modify its prediction and say the object is no longer there, and what happens if the knowledge is going to be like changed over time? That's what we expect as humans, right? So sometimes we think that something is true, and we verify it and see it's not, and we change our predictions. Because this system can do a learning for a lifetime, right? Lifelong learning. So it can modify its predictions.
Very good. Thank you, Amir.